Okay, so I'm very happy to be here. I guess everyone is very happy to be in Florence. Happy to open the 2024 GGI. Thanks to the organizers for this invitation. And I will be talking about effective field theories. Yeah? So that's the topic that is has been popular recently, but it's something that is pervading the entire physics, yeah, and has been around, yeah, for 100 of years. Yeah, so it's fair to say that without effective field theories, we wouldn't be able to do physics. Yeah, it's something that it's deeply ingrained in this framework of physics. So effective field theories, that's the idea is that we can focus on some particularly relevant variables for a given problem, and then we can integrate out all the remaining degrees of freedom, yeah, that are not relevant. And of course, yeah, if we couldn't do that, yeah, if we had to know the theory of everything, yeah, to calculate, know the motion of planets, yeah, or the spectrum of hydrogen, yeah, then there would never be any progress in physics, yeah. Einstein or Newton, yeah, wouldn't work it out. Yes, so the reasons why you can have this incremental progress, yeah, is that you can really write down a system. For example, when you describe motions of planets, yeah, you can write, you can describe it approximated by a point masses, yeah, with some force law. And you don't have to care about the internal structure of the planets, yeah, and so on to get the motions right. Then, if you want to do you can systematically improve these descriptions. Yeah, if for example tidal forces are important, yeah, you add another term to this force laws, yeah, and you work in some expansion and so on. So the fact, yeah, that we can do these approximations, yeah, it's something really extremely important in physics. Yeah, it's the basis, yeah, of what we do. So I would try to introduce this topic a little bit more systematically. Starting today, it will be today will be the introducing lecture. Yeah, I call it here Illustrated Philosophy of EFT. So basically, the best way I find to introduce an EFT is to show you a couple of examples, yeah, how this works, yeah, and then draw general lessons, yeah, based on this examples. So that's today. Tomorrow, yeah, we'll have a lecture about the particular EFT that is very important, yeah, for particle physics phenomenology. This is called SMEFT, Standard Model Effective Field Theory. This is an effective field theory extension of the standard model, by including interactions beyond the standard model. Next, the third lecture will be something more exotic, probably for most. Will be about non-relativistic EFTs. So when you go to very low energy, when your energy becomes comparable to when the energy of particles become comparable to their mass, so that you can use this high school notions like things like kinetic energy and stuff. So how do you describe it, yeah, in the usual quantum field theory language? Yeah, how you integrate out all this high frequency degrees of freedom from a particle. The fourth lecture is this famous touch of neutrinos that was mentioned in this title. I will talk. But that's also actually the topic that is very not much discussed, I think, in the literature. I will discuss how you use effective field theories to describe physics of neutrinos, in particular physics of neutrino oscillations. Yeah, so that's something. And finally, the fifth lecture will be probably the most experimental. Yeah, I will try to introduce you to on-shell methods in EFTs. So there will be later in the school lectures of Cliff Chung, yeah, who will certainly discuss the on-shell amplitudes methods to in much more detail. I don't know if you will talk about EFTs, this kind of EFTs in particular, yeah, but probably there will be also something about effective field theories. But nevertheless, yeah, let me just try to do a very brief, very quick introduction. It probably will be very sketchy, yeah, because we'll have to introduce a little bit of formalism and then try to understand the philosophy of how it works. Okay, so that's the plan of the lectures. Yeah, I mean, welcome, of course, to talk to me if you wanna hear about some other topics, maybe. Yeah, so I think that at this point, yeah, things have still can a little bit evolve. Yeah, so it's yeah. And also maybe not all of these topics. Yeah, I will have time to really talk about in depth. Notes, yeah, so there is, so you see that there is some lecture notes, yeah, that you might or might not have been shared with you already. I will. Okay, so Andrea will send an email, yeah, so this is like a draft version, yeah, of what I'm supposed to say here. So first thing, please don't share it, maybe because this is it's a document in progress. Yeah, for example, there is no references added properly. There is certainly there's many typos, and there might be some even some errors in it. But yeah, so it will be good if it's shared with you, especially for the next lectures, which may, at some points they might be a little bit more technical. So it's might be nice if you can look at this written notes, LaTeX notes, yeah, to see actually what's going on. And if you get lost, yeah, you can maybe find yourself back in this. So I hope that after this lectures, yeah, this will evolve into some more into some more neat and more organized document, yeah, that can be uploaded to archive or shared some other ways to the general public. Good. Conventions, I will not talk, maybe I will be introducing them as we go, yeah, so because it doesn't make sense to talk about everything now, but maybe one thing that I will mention, yeah, I will use the correct metric signature, yeah, if somebody is using the wrong one, yeah, it's please, yeah, that's a good moment, yeah, to change. And the h equals c equals 1, yeah, so it's the last time you'll see the speed of light and h bar, yeah, in this lecture, yeah, so that's yeah, and there will be, of course, I have a lot of quirky conventions. Yeah, probably I will be introducing them as we go along. Now, last thing, just before we start. Yeah, so there's a lot of good resources, of course, to learn more about EFTs, yeah, beyond what's in my lectures. There is some references that you'll find probably in this last section 1.7 of the notes. But maybe let me mention two of them that somehow I like the most, and they consciously or unconsciously influenced a lot my presentation. So that's one of them is lectures by David Kaplan, and that's interestingly it's in nuclear TH, you know, 0510-023, and that's I think Lezush lectures. Got 5 lectures on EFT. Beautiful introduction to EFTs. Another more technical but also interesting, yeah, because of these technicalities are also important, yeah, is by I.R. Rothstein. That's at pH 0308-266. Yeah, that's I think the TASI lectures, yeah, on EFTs. Yeah, so welcome to also to look at those lectures, yeah, because they contain a lot of interesting material. Okay, so let's start. Yeah, so let me just start with some example that is about for EFT or EFT philosophy, yeah, that you can actually explain to your grandmother. Yeah, so imagine that there is some collection of charges, yeah, and here a lot of they are contained in some region of size R. Then there is an observer that is very close to this region. So there is observer 1, and I will call him a near observer, and here L is for there R, and then there will be another observer here. Okay, I can use the whole blackboard at the distance R, and okay. There's probably already broken, so that's it. I don't know if I can make it. So now, if you are a near observer here, yeah, then you have to understand the electric field around you. You basically have to know the position of each charge. Yeah, so you have to write it, yeah, as a sum over all charges. Maybe there are a million of them, or a million of the particles with charges, and you have to write a potential as a sum of that. On the other hand, when you're far away, you don't have to do that. Yeah, so you can if you can learn from classical electrodynamics that you learned in school, that far away from this source, you can write it as you can write the potential, the electric potential, yeah, as a multiple expansion. Yeah? So there will be zeroth order term, which is the total electric charge contained here in this region. Then there will be first order correction. That will be the sorry, maybe let me write it like that. Whoops, and 1 over R, and then there will be another term let me write it like that, di dj 1 over R, and so on. So this nabla here, yeah, is a spatial derivative. Yeah, so, and these are some coefficients. This is the total charge. This is the dipole moment of the system. This is the quadrupole moment of the system. Yeah. So. As you see that as long as if you're far away from this collection of charges, you can actually capture the physics that is going on around you, yeah, without knowing the position, yeah, of every object here. But you just have a number of discrete parameters, yeah, that describe you the physics. So, and how many in principle, yeah, this expansion, yeah, is infinite. So you need an infinite number of parameters. But in practice, you just by dimensional analysis, yeah, you see that this dipole moment has to have has to have dimensions, yeah, of length, and since it's related to this system, you have to have that dipole moment is of the order of R, and then quadrupole moment is of the order of R squared, and so on. So what you have here is the expansion in the order parameter is big R, which is the size of the system, over small r, which is the distance here. So as long as this order parameter is smaller than 1, you might just need maybe just first term, maybe maybe you need dipole terms in the expansion, maybe quadrupole. That depends on the precision that you require. It also depends, yeah, whether, for example, the total charge vanishes or not, and so on. What is the leading order term? But typically, you will need very few terms to describe something that might be a very, very complicated system. And this is the Simplest example, yeah, of effective field theory, yeah, that is not even not even quantum field theory. Yeah, it's just classical. We condense something complicated, yeah, to something simpler, yeah, because we can, because these are the right degrees of freedom, yeah, at a given in a given regime, yeah, where this relation is satisfied. And you see, so for example, this far observer, yeah, it doesn't have to be a quantum field theorist, yeah, to do EFT. Yeah, so this is something natural. It could be an engineer, yeah, who knows nothing really about physics, just tuning the antenna, yeah. But intuitively, yeah, they will know that it's this is the right thing to do. Okay, so that's the illustration, yeah. So with the simple. Let's do some real quantum field theory. So let me now introduce you to give you another example of EFT, which I call, which will be a EFT for a single real scalar field, relativistic scalar field. So this is an ultimate spherical cow. There is not really that much application of that particular system, yeah, that I will talk about here, but it's so simple, yeah, that it will allow me to introduce some concepts of effective field theories, yeah, without doing too complicated calculations. So let's assume that the fundamental theory of the world, yeah, is described by two real scalars, yeah. So we have the kinetic terms. This is one scalar, and then there is another scalar. Sorry, it has a kinetic term, this has a mass term, and then there is another scalar that I will call h, and minus big M squared, h squared. Okay, so that's just the kinetic terms. We will assume, okay, I will call it M0 for the reasons that maybe will become clearer towards the end, that there is a hierarchy between these masses. So this H field is called H because it's heavy, and this phi is light. Yeah? So I will assume there will be some interaction between the two. So to make things a little bit simpler, I will assume that there is a Z2 symmetry acting on the light scalar that takes you phi to minus phi, so that I don't have to write too many interaction terms. So I don't write a cubic term, but I will write a quartic term. I will write interaction between where are you? Phi squared h, so like a interaction linear in field. Okay, sorry, let's try me to. And lambda 2 for phi squared h squared. So these are the interactions that I'm assuming here. So sorry, maybe for my writing, yeah, this is lambda. So that's if you see like a tenth, yeah, so that's supposed to be a lambda. Don't hesitate, yeah, if I don't write things clearly, yeah, to ask, yeah, and yeah, maybe that's another use, yeah, of the notes, yeah, so you can always click on there. Yeah, so after lambda 1 is m because it's a dimension full. So I just put some dimensions here explicitly, yeah, and that's the good. So this is this is a theory of two scalars, and now when you go to energies, yeah, that are much smaller than m. So now we are interested in energies much smaller than m. Well, when I say energies here, yeah, it means both energy and momentum. Typically, yeah, are small, yeah. So think about the 4 momentum all components for momentum, yeah, are small. Now, it's again intuitively, yeah, we expect that if you are in this regime, you cannot excite this heavy scalar. So it should be possible to describe physics just using the effective theory for a single scalar. So let's try to write it down. So what would it be? So it has to have a kinetic term like before, so we write it. And it will have a quartic interaction. Okay. What else? Yeah. So there is no reason, yeah, to stop here, yeah, because there is no reason that physics has to be renormalizable. Yeah, that's not the law of the universe. So we can continue, and we can write some, for example, minus C6 properly normalized, yeah, with phi 6, and then so on. So you see that. Okay, sorry. So you see that I wrote this Lagrangian in some expansion. Yeah. So the expansion is according to canonical dimensions of the interaction. So this, yeah. So the basic thing about EFT, yeah, is to count dimensions. Yeah. So we know that action is dimensionless. Yeah, because in the path integral it goes like e to I. Path integral is integral over e to I s, so s has to be dimensionless. So it means that Lagrangian has to have dimension mass to the 4, so that because s is the integral over d4x Lagrangian, yeah, and x has a dimension of 1 over mass. Yeah, we are using, remember, natural units. There is no, so distance is 1 over mass. So this so we can look here. Yeah? So m has dimension of mass. So in order for this term to have a dimension of, for Lagrangian to have a dimension mass to the 4, it follows immediately that dimension of psi has to be mass to the power of 1. Yeah? So then it follows that the dimension of a derivative is also mass, because it's 1 over dx. So the dimension of that is also 4, so we already fine. Here, phi to the 4th has a dimension of 4, so this accounts for the Lagrangian will have. So this has dimension 4. So the Lagrangian will have a dimension 4 if lambda has dimension 1. I mean, it's more and more tenth and then lambda. Okay, and here phi to the 6 has already dimension to the mass to the 6. So to get the correct dimensions, we have to have a mass 1 over mass squared. And so on. So if I wrote a dimension 8 term, yeah, it would have 1 of mass of dimension, the Wilson coefficients, because in the EFT, yeah, we use this jargon, yeah, that we don't call couplings, but we call them Wilson coefficients, yeah, to sound a little bit more noble. This Wilson coefficient, yeah, will have dimensions of inverse mass. So now this makes sense, yeah, if the dimension, yeah, of a CI is so the dimension of a CI, it has a, oh, maybe let me write it like that. Dimension of a CI has mass over 4 minus I, and if we now we identify this mass scale with the heavy mass scale of the heavy scalar, then we can write that Ci, yeah, has m of 4 minus I. And then if we write some amplitudes for some process, yeah, we'll have a, it will be of this, it will have to be of this form, that it's sum over Wilson coefficient C. And because of dimensional reasons, yeah, this has to be, because the amplitude is dimensionless. So if this has dimensions of mass to the 4 minus I, this has to be, yeah, the dimension of I minus 4. So, and then we sum over I. So we see that this is an expansion, yeah, in an E over M. So the higher the dimension, the bigger is the suppression. So if E over M is much less than 1, this is some series that has a chance of being a convergent. So this kind of setting, yeah, is has a chance to work, yeah, if we work at an energies much less than M, which is the regime, yeah, of the EFT we have chosen. Okay, so this is not the only way how to build a power counting, so-called power counting of EFT. Yeah, so we can, but it's one of the very common ways. Yeah, so we build an expansion according to canonical dimension of the field, and as long as we are working at energy mass much lower than the heavy mass scale that sets the scale of this Wilson coefficients, yeah, this is a convergent expansion, and our EFT is in the validity regime. So okay, so now let me stop for a moment. Let me stop for a moment here and ask a question. So, is this the most general Lagrangian that I can write here, subject to this Z2 symmetry? Are there any other terms that I could write beyond the ones that I already? Because when we build an EFT, in general, we should be agnostic, and everything that is allowed, yeah, by the rules, yeah, it should be included. So, for example, I can see that I clearly forgotten many possible interactions here. Yeah? So, for example, I forgot delta lambda is equal to C6 twiddle over 6 phi cube box, where box is the d mu. Yeah? Why didn't I write this term in this Lagrangian? Is there anyone who knows already?
I have no idea how it can be generated from the original theory.
Oh, well, it can be generated, but yeah. Anyway, so the answer is that this term is redundant. Yeah, that's very good. And this is again a very, very important concept in general in QFT, but especially in EFTs, that there are certain equivalence classes of operators. Again, in EFT we often don't call interactions, but we call them operators. Yes, so again, just to sound a little bit more noble. Then, so why is this redundant? The way the quick way you can see that it's redundant is because it can be removed by a field redefinition. So it should be intuitive, and it was proven by some papers, some obscure, not very well-known papers, yeah, from I think 70s and 80s, that your amplitudes calculated in quantum field theory, they don't depend on the parametrization, on the change of variables, yeah, in your QFT. So, for example, if I make this kind of change of variables, phi goes to phi 1 plus here, alpha phi squared. So I shift my field by a cubic term, and I'm assuming here that this is something that is some something small, yeah. So this is something perturbative, yeah. So this way, I don't really change the kinetic terms, yeah. So but I will change interaction terms. So the shifted Lagrangian will describe the same physics, yeah, as the unshifted Lagrangian, yeah, in the sense that the amplitudes that calculated for both Lagrangians are the same. So if I do that, you can see that what will happen to the kinetic term. The kinetic term will have 1/2 d mu phi squared will shift into the same and then plus something that is proportional to alpha, actually minus, yeah, because I will want to write it as alpha phi cube d phi, and then something order alpha squared. So that's why I was assuming that it's small, so that I don't have to like go farther in this expansion. So you see, if I now choose alpha is equal to C6 twiddle over 4, yeah, you can see that this term can be removed from the Lagrangian, yeah, by this field redefinition. So I don't have to write it. I can. I mean, if I could keep it and I could carry it around, carry it along with me, but I don't have to because it's redundant, because it can be removed. But you can one thing to notice is that maybe that is also quite important, that the effect, it's not that this term doesn't do anything, because when you do this shift, it's actually its effect will be reabsorbed in other terms that are already present here. Why? Because, for example, if I now shift minus 1/2 m squared phi squared, yeah, it will be the same minus alpha m squared and phi to the 4th. So you see that, and this is equal to minus C6 over 4 m squared 5. So you see that when I do this kind of shift, the effect, part of the effect of this C6 twiddle now reemerges as a quartic coupling, as a shift of the quartic coupling in this. Yeah? So this has the same form as this. So this corresponds to a shift lambda goes to lambda plus m squared C6 twiddle, right? So, but it's not all, because now I should also, sorry, I'm operating here in the Windows method. Yeah, if you, it's a little bit obsolete, but yeah, if this becomes too messy, yeah, let me know. I know what to do. So what happens to the quartic term itself? Yeah. So this shifts to the same plus minus lambda alpha over 3 phi to the 6, and so it's equal to minus lambda C6 twiddle and over 3 so the 6. So another effect is that when I shift the quartic term, I generate the, how do you call it, sextic term. You generate phi to the 6th term. That's the correct way to say. So you see that this is not. It's not that this doesn't have any effect. It has an effect. So this is like having a C6. So if you can convince yourself that if you work out here this normalization, that this is the same as C4. Oh, so sorry. Lambda. I was calling this lambda. My notes is C4, but okay. Okay, so it's not that it doesn't have any effect. It has an effect as it's this kind of operator is like having a quartic and phi to the sixth term at the same time. It's like a coherent action, of these two terms. So this is this is the this is what happens here in EFTs, that you have these redundant operators that you can shoot them around. And you see that this is actually, you can do it in both ways, So you can, you could at the same time, you can actually use this shift to get rid of this term and generate this term in the Lagrangian. So this means that you could have different bases of your EFT. This is another piece of important jargon. You could work with a basis, where of dimension 6 operators in your single scalar EFT, where your operator is phi to the 6. Or you could work in another basis where the operator is phi, the dimension 6 operator that you work with is phi cube box phi. And these are not the only possibilities. There's several more possibilities that you could write. The nice thing in this example is that the basis is one-dimensional, so you just only have one, the equivalence class has one element, and this is not always the case, and when you go to SMEFT, you will see that, the sky is the limit, so it can be, there can be many, the basis can be multi-dimensional. But in this example, it's simple, but, let me just do the last method of windows, So maybe I can leave it as an exercise because I think Roberto told me that I should give some exercises too. What if you have your operator is this? C6 hat. If you add such an operator to your Lagrangian, so box phi squared, that's also a dimension 6 operator, because we have two dimensions, So box has dimension mass squared, this has dimension mass, so this all has dimension 6, so this has to have dimension 1 over mass squared. And you can show that this operator is also equivalent either to this operator or to this operator by a suitable field redefinition. So you could also work with, the phi 6, I can call it unbox basis, or in the box basis, or in the double box basis. You can have several, at least 3 different natural bases, of your EFT here. Okay, how is it going? So I'll I'll go on for another 15 minutes, before the break, because we started later. Good. So next thing, after this important intermission, let's continue. So we want to match these two theories, the theory with one light and one heavy scalar to the EFT with just a single scalar. So what we should do, basically what we have to do is to calculate scattering amplitudes in both theories. We calculate scattering amplitudes for the light fields, because that's what we are interested in. We cannot excite the heavy fields, so we have to calculate scattering amplitudes for the light fields. So for example, we calculate a quartic amplitude in the EFT. This is phi, 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 and phi. And this will be mediated by this lambda. And we could calculate the same amplitude in that would be EFT. We could calculate the same amplitude in the UV theory. It will also have a quartic term, but possibly with a different, here we have a lambda, and here we have a lambda 0. But it's not the only possibility. For example, we'll also have this kind of diagram where we exchange a heavy field here. So in the UV theory, we'll have more diagrams. And with this, we have to say that this amplitude, MEFT, is equal to MUV. How is it possible? Of course, it's not possible. So it's possible because here in EFT we have in fact infinite number of terms. Yeah, but what we do in practice, yeah, we're gonna take this UV amplitude and we will expand it in powers of 1 over m, so that we can match order by order here in the EFT, so that we can first match the lambda and then we will match the C6 term and so on. So this is what you do, and this process can be easily automatized. There's, for example, on the market there is something that is called so this process of equating the parameters of EFT and its UV completion is called matching, and obviously the program that automatizes matching is called matchmaker. So you can do it automatically, but yeah. Oh, sorry. Yes. Yeah, so indeed. Thank you. Good question. Yeah. So I will come back to it in a sec. Yeah. I mean, like probably second will be more than 5 minutes, but okay. But yeah, this is what I showed was a tree-level matching. But this matching can be systematically improved to any loop order. Yeah. So then we could, so this is a matching at tree level. So maybe we can add some indices 0. But then we can go to loop level and calculate loops both in the EFT and in the UV theory. And again, we will expand in 1 over m and match the coefficients, yeah, in the two theories. So this is So this is what you do in principle. This is a little bit. This might be a little bit pesky to do, yeah, because especially on the UV side, you'll have a lot of diagrams when you want to match phi to the 6. Yeah, you will have, it will get a little bit complicated. So fortunately at tree level, there is a very useful hack, yeah, to avoid it. This is related to some existence of the functional methods of deriving EFTs. So instead of calculating amplitudes, you can do something very simple. You take the UV Lagrangian, you calculate the equations of motion for the heavy field as a function of the light fields. Yeah? So you solve the equation of motion, and then you put the solution back into the Lagrangian. So I will not prove that this is this is equivalent, but the proof is quite simple. Usually, the best thing is to go via path integrals, yeah, and then the leading term, yeah, in the matching, yeah, in the path integral language, yeah, will be the extreme point, yeah, of the Lagrangian. Yeah. So it's fairly simple to prove. So this is what we do, and so just to see what this will give us. So let's do that. So equation of motion for the heavy field here will be the following. You get box plus m squared plus lambda 2 phi squared over 2 h is equal to minus lambda 1 m over 2 phi squared. So that's the equation of motion. So how do I solve it? Yeah, so I hope this is clear. Yeah, so this part comes from the terms that are quadratic in h, and because we have this linear in h term, which is sort of what gives you this kind of diagrams, we also have the right-hand side, yeah, that is proportional to this interaction term. So how do we solve it? Yeah, we solve it like any physicist does. So we just divide the two sides, yeah, by, so we have a solution is minus lambda 1 m over 2 box plus m squared plus lambda 2 phi squared over 2 minus 1 phi squared. Yeah, this is solved. But what we want to do really, yeah, so now we can put it back, or maybe let's do this one last step. We put it back into the Lagrangian. So you can see that if you put it in this term, you will get basically phi squared and then this inverse inverse of this bracket and then phi squared. So lambda EFT at tree level will be given by, wait, where are we here? So it will be given by the light, so when we plug in this H, yeah, so of course we don't touch the light field, so there will be a, maybe I'll move to the new blackboard then. Maybe too many things to write. Let's erase the engineers now and let's do good. So lambda EFT 0 we'll have this d mu phi squared minus m squared, minus 0 squared phi squared. And then there will be minus lambda over 4 cubed phi to the 4. And then when we plug this h into this term, yeah, we'll get something that is lambda 1 squared m squared over 8 phi squared m squared plus box plus lambda 2 phi squared over 2 minus 1 phi squared. And this will give me, So when I plug in this term, I will get plus 1 over 4, but I also have to plug it, yeah, in all the other terms, and it's easy to convince yourself it's always just the same case that these other terms will give you the same, but with an opposite sign and minus 1/2. So at the end of the day, you will get 1/8 here, yeah, so. But you see that this kind of structure, so I just wanted to show you that this kind of structure emerges. And so now what it is, yeah, so that this is something looks very complicated and non-local, but remember that our goal is to actually match it to this Lagrangian, EFT Lagrangian, that is organized in the dimensional expansion. So we can expand it. So we take m squared out, and that will conveniently cancel this m squared. So I will just follow this last term, and lambda squared over 8 phi squared, and then I have to expand 1 plus delta over m squared plus lambda 2 phi squared over 2 minus 1. So this will be equal to 1 minus delta m squared plus lambda 2 phi squared over 2 m squared, and then phi squared, and then plus order m to the minus 4th. I'm not writing, yes, please? Yeah? No? Okay, so it was this. So I'm not writing this expansion further, this 1 over n to the 4th terms and so on, because there is no, I mean, I'm not interested in this. I mean, I could, but I'm not interested in dimension 8 and higher operators. So subsequent terms in this expansion will give me dimension 8 operators. And let me see what I get here. The first term gives me phi squared times phi squared. That gives me a phi to the 4th term. And so you can maybe just write it more clearly. Lambda 1 phi to the 4th over 8. And then I have lambda 1 squared over 8 m squared phi squared box phi squared. And then it should be minus, yeah? Minus lambda square 1 squared lambda 2 over 16 m squared phi to the 6 plus order m minus 4th. So you see that what I got here from this integrating out is that integrating out heavy scalar will contribute me to the quartic term. So the quartic term in the EFT, which I denoted as conveniently as lambda, is not the same as the quartic term in the UV theory, which is lambda 0. They are related by where's my 4, 5? No. Here. These are okay. They will be related by lambda is equal to lambda 0 minus 3 lambda 1 squared. This 3 is because the normalization is 1 over 24. Yeah, so in the EFT Lagrange. You see that also getting the 6 term. So I'm getting C6 is equal to 45 lambda 1 squared lambda 2 over m squared. And then again 45 is, if you divide 6 factorial over 16, you'll get 45. You can quickly do this calculation in your head. I did it before, but you can.
Sorry, just double check. So this factor of -3, it comes from removing this
No. The factor of 3 just comes from this because in the EFT Lagrangian, which is here, I define the operator which is normalized by 1 over 4 factorial, and I only got 1 over 8 here, so I have to, And then it's the same reason for this 45. And now I also have something that I don't have in this EFT Lagrangian. So I have to, you see that, unfortunately, this is this thing that so there is this discussion of bases, that there is, you should only use, you use only non-redundant set of operators. But when you actually do the integration of the heavy degrees of freedom, you typically get different redundant operators. And then you have to project it, to some bases, So for example, we first have to. So what is this operator? So this is a dimension 6 operator, but we haven't seen it before. So let me open another window here, and you can write it. So you solve box phi squared. You can write it, that this is 2 phi squared d mu phi. Of phi cubed d mu phi, phi squared and d mu phi times phi, and then it's equal to 2 phi cube box phi plus 2 phi squared d mu phi squared. So this guy is already the one that we discussed in this context, of the box basis. So we know what it is. So, and this one, the way you deal with it is you can write it, for example, that phi squared d mu phi squared is equal to minus 2. So I integrate by parts, and minus 2 phi d mu phi times. So let me just write it like that, d mu phi. I take this derivative by parts, and it will be minus 2 phi d mu phi squared minus phi squared box phi. And you see that what I got here after integration by parts is the same. So at the end of the day, phi squared d mu phi squared is equal to minus 1/3 phi squared box phi squared. And sorry, phi cube. sorry, it's minus 1/3 phi cube box phi. Oh, sorry. So once again, just so I integrate by parts. I can hit this, and I get the same term as with the -2 after integration by parts, or I hit this derivative, and I get phi cube box phi, and then I can write this relation. So then I can put it back here, and then I can write that phi squared box phi squared is equal to 2 minus 2/3, so it's 4/3 phi cube box phi. So you see that we get all the dimension 6 operator here. Good. So so you can write that the result of this matching is C6 is equal to minus 4 lambda 1 squared over m squared. Yeah, so we got this. This operator, we have to we'll get 1/6, and we have to get 1/24. So yes, there will be a factor of 4. So we get this with some coefficients in the EFT, and now by using this map between what C6 and C, we can project it back, yeah, to the either this basis, phi 6 basis, or the other basis, whichever you want. Let me just click so that I don't write any more to the yeah, and the final wait. This is here. And the final answer is for the matching of the coefficients between the two theories. Sorry, that in the notes instead of lambda I write C4, but the C4, so C4 and lambda is the same thing. So the mass term doesn't change. The mass term is the same at tree level in the UV theory and the EFT. The quartic term is related in an already trivial way, and then the phi to the 6th term is related in this way, so to the parameters of the EFT. And you can continue this to higher dimension operators if you want. So this is the result of the tree-level matching. So you see that all this, like the EFT techniques that you use later in different contexts, they just pop up here. Let me just, before the break, let me tell you that you can do the same thing at loop level. So if you do at one loop level, this is what you get. So here the results are only in the limit lambda 1 is equal to 0, so because otherwise the formulas are very lengthy, I didn't want to display them. But of course you can calculate it in any case. You see that then the parameters in the EFT become they are dependent on the renormalization scale, because there will be infinities that you have to subtract by counter terms, and then you will get these logs of normalization scale mu. So in principle, the parameters in the EFT will become the running parameters, depending on some arbitrary scale mu. For C6, this is not the case. You're just getting that they are 1/m². So now, what do you do with these logarithms? So in general, this appearance of logarithms, in perturbation theory is not good. If you have large hierarchy of scales, because logarithm can be large, and even if your theory is perturbative, you multiply the small coupling by a large logarithm, then it becomes badly convergent. So the best way is to get rid of the logarithm. So you see that if you do the matching, the best thing to do is to put mu equal to the heavy mass scale. So you match with the EFT at the heavy mass scale, or at the large scale, and then you can pull down your EFT coefficient to the low scale where you do your experiments by RG running. This way, you resum all these large logs into renormalization group running equation. So for example, if you do that for the mass term, you will get something So these are the RG equation that you will get in this. And for example, for the mass term, yeah, you will get this kind of solutions, yeah, where all these large logs can be resummed. So this this is actually another strength of the EFT that tells you that it's not only more simpler to work with a single EFT, scalar EFT instead of two scalars if you're at low energies, but it's also better from the calculational point of view. Because if you do a calculation, if you try to use the full fundamental theory, the theory of everything, yeah, which is the theory of two scalars here, to calculate phi scattering at low energies, in your perturbation theory, there will be these logs of the heavy mass scale over the small energy, and that will make your perturbation theory badly convergent. On the other hand, if you integrate out the heavy scalar, you match at the heavy scale, and then you run down the parameters down to low scale, just the parameters of the EFT using the RG equations, then all these large logs are gone. Yeah, they are resummed into the RG running, yeah, of the Wilson coefficients in the EFT. So that's the practical reason why actually using EFT is better than using the full theory of everything to calculate specific process. And that's something, of course, that has been known for long ago. People were doing, for example, heavy flavor physics. Yeah, they were using it all along. Yeah, people. Yeah. Even when people doing supersymmetry, at some point they realized that because supersymmetry is so heavy, yeah, it's better to go to the EFT, yeah, where the SUSY particles, yeah, are decoupled, and then you can do calculations, yeah, much more reliably. So EFTs, yeah, is not only convenience tool, yeah, but it's also a practical calculational tool that makes your life much simpler. Okay, let's do the break, yeah, and then I will go through more examples, yeah, with less detail, but yeah, it's more. 15 minutes, yeah, or maybe 10 minutes, yeah, because 10 minutes, yeah. 30 past. Okay, so let's continue. So maybe before going to the next topic, maybe I forgot probably one important thing about this spherical cow scalar. So if you look at the matching between the parameter m squared in the EFT and the parameter m, the light scalar mass in the full theory, you see that it has this form. If you choose your randomization scale, as I said, that to minimize these logs, you get this. You see that actually, by the dimensional analysis, you would expect, yeah, that in the EFT, this small m is of the order. If you do the power counting, and you say that this is at the term of dimension 2, so it should be of the order of the big scale m to power. Yeah? So small m should be of the order of m by naive dimensional analysis. Of course, it cannot be, because otherwise we cannot do EFT. And this sort of this contradiction, yeah, is called the hierarchy problem. Hierarchy problem is something that can be best explained in the EFT setting, yeah, because that's where you already see it, yeah. In the standard model, strictly speaking, yeah, there is no hierarchy problem, yeah, because it's a regularization-dependent statement. But as soon as you match your EFT to some higher, some more complete theory, more fundamental theory, you will see that your mass parameters, if they are not protected by symmetries, like in this case, they will receive contributions that are consistent with naive dimensional analysis. In this case, the EFT parameter m receives contribution proportional to the big M, only suppressed by the loop factor. So if lambda 2, let's say lambda 2 is also order 1, yeah, this will be the hierarchy problem. Yeah, if lambda 2 was smaller, yeah, that would be so. So in order, yeah, to have a small m, you will have to fine tune between these two contributions, and that will give you the so the only way to get a light scalar, yeah, in this case, yeah, will be to perform fine tuning, yeah, between. So assume that m0 is large, m is large, and they cancel each other, so that small m is accidentally small. And that's so in the EFT, this hierarchy problem is something that is seen, that is calculable, yeah, that you can define, yeah, how much fine tuning you want. It's not a regularization dependent statement. It's something that is really there. Okay, so let me finish with the spherical cow and move to some EFTs, yeah, that are of interest, phenomenological interest. So next topic, yeah, is something that is called Euler-Heisenberg EFT. So, like Euler is not the Euler mathematician, yeah. So, and Heisenberg is not the one from Breaking Bad, yeah. So it's so this is Euler-Heisenberg EFT is the theory of light, of only light. So imagine that you are you consider, yeah, for example, propagation of electromagnetic waves at very low energy. So basically, your radio waves, yeah, or anything. Low energy means below the electron mass. Yeah, so we are at energies less than electron mass. Then there is there is just light, yeah, at this energy scales. Yeah, you cannot create electron-positron pairs. Let's say you don't have electrons around. You are in the region of space where there is no electrons around. So the only degrees of freedom is photon, a mu. But you still need gauge invariance, yeah. So because a mu. So a mu transforms under gauge symmetry. Yeah, it has 4 components, and the light has only 2 polarizations. So you need gauge invariance to decouple the unphysical degrees of freedom. So actually, you have to build your theory not from a mu but from f mu nu. Yeah, that will be a gauge invariant object. You cannot make gauge invariant objects, yeah, from a mu alone. So that's almost true. Yeah. So there is f mu nu. And then you can also define f mu dual, which is also gauge invariant. Alpha, beta, f, alpha, beta. Another piece of my conventions, yeah, so here you see what I did. I don't care about where the indices are, yeah, so that's my quirk, yeah, so there is no, when you do Lorentz invariance, yeah, makes it completely unambiguous, yeah, so only when you have to really resolve it into some components, yeah, you have to be careful about. But yeah, it's, for example, it's more. I should write it like that, yeah, to be more proper, yeah. But I often don't care and just write it like that, yeah. So and then you should in your head you can always put the indices, yeah, in the right place, yeah. But this Lorentz contractions, yeah, are always unambiguous, yeah. So there is not really need to use these conventions, yeah, that you only, for example, that you only contract upper and lower indices, yeah. The indices are always contracted, yeah, with Minkowski tensor. Okay, so how do we write an EFT of light only? Yeah, so the first term, the lowest order term that we can write is this. And this gives us Maxwell electrodynamics, the one that we had in school, yeah, with all these plates and antennas and so on. So that's not very interesting, but there's no reason you don't have to stop here. We can, just like in the case of the spherical cow scalar, we can build our Lagrangian, yeah, in dimensional expansion. So the next order term, yeah. So what we could write? We could try to write something like this: f nu rho, f rho mu, like contraction like this. But this turns out to be 0 if you use integration by parts and so on, yeah, or rather, I mean, there is a simpler way, yeah. So this is a symmetric tensor, yeah, and it's contracted, yeah, with the antisymmetric tensor, yeah, here. So that's general theorem that all contractions of f with the odd number of f's will be 0, yeah. So you have to go to Young-Mills theories to have this kind of invariance. So actually, the next thing that you can write is this. That's a dimension 8 operator. So let's do the dimensions, yeah, again. So a mu is like all bosonic fields has dimension 1. There are 2 derivatives here and 2 a's, yeah. So this has dimension 4 as it should be. And so because this has dimension 4, f mu nu squared has dimension 8. So this Wilson coefficient, say E, has dimension of 1 over mass to the 4. Yeah. And C2, f mu nu twiddle. So you can also write this kind of invariant. And now these two are independent. Yeah, there is no field redefinition. Yeah, that will can remove one of these two and not produce something else. But you can show that there are several other operators you could imagine. Yeah, so for example, you could imagine something like f mu nu, f nu. Okay, f mu alpha, f alpha nu, f mu beta, f beta nu. That's something like that. It's not, again, it's not, it's a redundant operator. You can express it. So that could be an exercise, yeah, that you can express this kind of operator in terms of these two. Yeah, so there is no, this is a complete basis of dimension 8 operators. And then, of course, you could go further, but for the moment, there is no need to go further. So you see that this Wilson coefficients have dimension 1 over mass to the 4. So what is this mass scale now that sets the name? So if, I mean, we are will be assuming, like, I mean, it's not an assumption. We know that electrons exist. So we should. So if we integrated out electrons, then this Wilson coefficients, yeah, have to be of the order of 1 over m electron to the 4th, yeah, because that's the only mass scale that we have. Yeah? Now we don't have any other mass scale. So we already, without calculation, we know it. Now, to a little sharpen it a little bit, we would have to say, so how these are generated. So this is an operator with 4 fields, yeah, 4 fields and 4 derivatives. So you would, in order to match, you would have to, we have to match it to some diagram in QED. Yeah, so the UV completion of this theory is the more fundamental theory is QED, and then of course you don't have anything like that. Yeah, in QED, yeah, you don't have electron coupled to photons, so that doesn't exist. So you have to go to the loop level, and then at the loop level you can write a diagram like this. Yeah? So you see that you will have 4 powers of electric coupling that will appear, because if you match it, yeah, there will be each photon coupling here, yeah, will result in a electric coupling E appearing here, and you will have a loop factor, yeah, so 1 over 16 pi squared. So this equals alpha squared over m e to the 4th. So we know without any calculation that this has to be the order of magnitude, yeah, of this Wilson coefficients of this theory. And now if you do the calculation of these loops, so you do the same thing. So okay, here we cannot use this trick, yeah, with equation of motions, because this doesn't work for loop matching. So we will have to calculate the loops. We have to calculate the loops in QED, and then we have to calculate the tree-level amplitude in the Euler-Heisenberg theory. Require that the loop in QED in the expansion in 1 over electron mass is equal to this amplitude, and then we'll get the practical value of Wilson coefficients, and then we'll get something that is C1 is equal to, where is my, it should be here. Oh. Here, this alpha squared. So it's very funny, but I just write it down so that you see that it's really there. Somebody calculated it. Sorry. C1. Okay, let's do times 8, and C2 is the same times 14. Just numbers, random numbers, yeah, generator, yeah, this is what comes out. So QED corresponds, so at low energies, reduces to Euler-Heisenberg Lagrangian. with a particular values of C1, C2 that you can. But then you can maybe have a little bit more global view of that, yeah, because we know that electrons exist, but maybe there's something else exists too that we don't know of, yeah? So for example, if there is some scalar in the nitrogen that has a charge, it probably cannot be light scalar with a charge, but maybe it can be a light scalar with a milli charge, yeah, with a very, very small electric charge that can exist. Then it would give you these two Wilson coefficients. And then the values would be like this. Alpha squared qs to the fourth over ms fourth, qs to the fourth over ms to the fourth, and 8, 14, no, sorry, 7 and 1. Another random number generator. You see that the pattern is different, yeah? So for example, QED gives you C2 bigger than C1, but scalar gives you C1 bigger than C2, yeah? So there is some, you are in this kind of, there is another possibility, you could have a you could have a UV completion of Euler-Heisenberg, which is itself an EFT, which is an EFT of an axion. So you could have a theory where you have an axion-like particle coupled to, like for example, via alpha over 4 pi f. Sorry, it's a sec. Let's do it like this: Ca a f mu nu dual. C. So this is axion field. This is FF dual axion. That's how axions like to couple, yeah. Unless they are more axion-like, they could also couple to. I mean, so some you can also have models here where they also couple to F squared, yeah. But that would be a different thing. Anyway, that when you integrate it out, that's very easy to see. As the equation of motion, yeah, for the A will give you. On the right-hand side, will give you FF dual, and then you put it back into Lagrangian, and you will get FF dual squared. So you will get this Wilson coefficient. Yeah? So axion will give you C1 axion and C2 axion. C1 will be 0, and C2 will have some value which is unknown. Yeah, Ca squared alpha squared over 2 pi squared ma squared f squared, where f is the scale that enters in this non-normalizable interaction of the axis. So globally, yeah, you have this kind of you have a parameter space, yeah, with C1 and C2, yeah. So QED is here, yeah, but then you could also have some fermion that is like electron, but yeah, with a different charge or different mass. So it could take you like somewhere in this direction. So that would be fermion. Or if you have an axion, you could shift yourself towards larger C2. That would be axion. That would be a fermion. And the scalar would shift you somewhere here. Yeah. So that's QED point. And this. So in principle, it would be interesting to actually measure this C1 and C2 from experiment. Yeah. And very surprisingly, these parameters have never been measured yeah? So I think the closest they got to this is the PVLAS experiment, yeah, in Italy, but they didn't have enough sensitivity to see the signal. There is some claims from astrophysics, yeah, that they observe this kind of effects, but this is very messy, and yeah, that's not really, and there's no really measurement of C1 and C2. They just say that they see their effects. So how do you see these effects? Yeah. So in principle, you could take photons, yeah, and scatter them at very low energies and measure C1, C2. But that's not we don't have photon colliders, and this is very weak interaction, yeah. So at low energies, yeah. So it's not a very practical thing to do. Also, I mean, photon scattering is something that is common in colliders. Yeah, so this is a process that you take into account to predict your backgrounds and anything. But in colliders, yeah, photons have very large energies, like GV energies, and this Euler-Heisenberg EFT, you can use it at below the electron mass, so below MeV, or 2 electron mass at least, yeah, so below MeV. So at such low energies, there is no measurements of photon scattering. But what does it do? So you see that actually this terms. So what you could try to do is try to see how this interaction terms in the Euler-Heisenberg-Lagrange, how do they modify the propagation of electromagnetic waves? So what they will do is that you will get some non-linearities, yeah, in the Maxwell equations, yeah. So you are told, yeah, that Maxwell equations, yeah, are linear, yeah, and that when the superposition of two solutions is also a solution. But if you go deeper into this rabbit hole, yeah, there is this effects due to virtual electron pairs, yeah, that are described by these two terms in the Euler-Heisenberg-Lagrangian, and this will give you nonlinear effects in electrodynamics. Yeah, so in principle, yeah, this linearity of electrodynamics is only an approximation. So how do we actually can search for these effects? Yeah, this is so the you could maybe it will help, yeah, if you rewrite this Lagrangian in more like engineer-friendly variables. Yeah, so for example, yeah, so you have F0 k is epsilon k, F KL is minus epsilon L KLM BM, and then F tilde 0k is equal to bk, and F tilde KL is epsilon KLM epsilon m. And then you will get that this Lagrangian can be written as, okay, maybe I'll go to the correct section in the notes, yeah, so because it should finish soon, so that will let me just write it. So you can write it like that. So you see that it's s squared minus y squared and plus, and then this one of this Euler-Heisenberg terms gives you this correction, and then the other gives you, so f dual is E times B. Yeah? So now you can calculate, what will happen is that you can calculate, for example, electric displacement vector or magnetic intensity vector, yeah, as, from this Lagrangian. And then in vacuum, you should have D equals E and H equals B. But because of these nonlinearities, you will get these additional terms. Yeah? So the relation between the D and E and H equals B is not the simple relation, but it's as if vacuum has become a medium, which is polarizable and magnetizable. So the D is not equal E anymore, and H is equal B. H is not equal B anymore. So this you can now you can imagine that you have a, for example, so how to observe these effects? Yeah, you can imagine that you have electromagnetic waves that goes via the in this vacuum, yeah, which is polarizable and magnetizable, and then you put a magnetic field, yeah, into external magnetic field into this. So, and then you expand, so B0 is large, and then there is a small perturbation of a wave. So if you just write it to this thing to leading order in the small perturbation of the wave, you will get something like that. Yeah. So the relation between the D and E, yeah, becomes this, and it depends on the relative direction between the electromagnetic wave, so the E vectors and B vectors, and the direction of the magnetic field. So if you put, for example, if you put electric field is polarized in a specific direction, then this will be non-zero. But then, because B is perpendicular to E, so if this is non-zero, so if E is polarized, if E is parallel to B0, then this will be non-zero, but this will be zero. On the other hand, if E is perpendicular to B, then this will be zero, but this will be non-zero. So the vacuum, so the jargon is here that the vacuum becomes birefringent. So the propagation of electromagnetic waves will depend on the polarization. And the relation between the D and E will give you, epsilons, how they are called, permittivity and permeability. I mean, who invents this? But yeah, there is epsilon and mu. Yeah, let's call them epsilon and mu. So for a perpendicular, so I call the polarization of the waves is the direction of the electric field, and if the electric field is perpendicular to the magnetic field, you will get this epsilon and mu, and if it's parallel, you will get this epsilon and mu. Then the refraction index is a square root of that, and then so you just have to multiply the two and then expand in C1, because C1 is C1 B0 is squared is assumed to be something small, and then you will get this expression. So that the refractive index, which is inverse of the speed of the electromagnetic wave, is corrected by this Wilson coefficients. And the effect depends on this Wilson coefficients, which are order 1 over me to the 4th, and magnetic field, which is B0 squared. So unfortunately, magnetic fields, we're not very good in creating magnetic fields. Yeah, so the best we can do is some poor 10 Tesla in LHC, and this in natural units, 1 Tesla is 10 to minus 10, 1 over MeV to, sorry, 10 to minus 10 MeV squared. So 10 to minus 10. So you need 10 to 9 Tesla to be close to ME squared, so that this, and the C1 is 1 over ME to the 4th, yeah? So you really need, we need very large magnetic fields for this effect to be large. So of course you don't observe it. With the 1 Tesla fields that we can, or 10 Tesla fields that we can produce, this will give us a very, very suppressed effect. But people still search for it, yeah? So that's why we haven't found it yet. But people search for it. It's some sort of a holy grail in this laser and magnetic field communities. Yeah, so if we found it, yeah, we could see that different polarization, yeah, of light propagated different speeds. Note something interesting. The last thing that I will just say, yeah, before I finish, is that this C1 and C2, yeah, so this speed of light in a magnetic field cannot be larger than the speed of light, of course. So this n has to be larger than 1, because the velocity of the wave is 1 over n. So n has to be larger than 1. Otherwise, if n was smaller than 1, then we could send superluminal signals around the LHC ring and then kill maybe not our grandfather, but yeah, our colleague. Yeah, from I know, no, we can do it. But that's a bad example. Yeah, but we can go to the past and then kill someone. Yeah, who didn't cite us. Yeah, that's the paradox. Yeah. Anyway, this has to be. So it means that C1 and C2 are not arbitrary. So you think that when you do EFTs, yeah, anything goes. Any of these interactions should be is allowed, but no. If C1 and C2 both have to be positive, otherwise we get a contradiction or we get a paradox. So this C1 and C2 cannot be negative. And fortunately, QED gives you positive C1, C2. Scalar gives you positive C1, C2. The axion also gives you positive, at least not strictly positive, but positive C2 and 0 contribution to C1. So it is not any physics that makes sense will give us positive C1, C2. So this is an example of a positivity. That is another important concept in EFTs. This is one way to prove positivities of C1 and C2. The other way is to use analyticity properties of the amplitudes, yeah, and then write dispersion relations based on that. And then one can also prove it without actually using any engineer's variables, yeah. But you can use it. Just based on axioms of QFT. But yeah, C1 and C2. This is what the C1 and C2 are one of the examples, yeah, of positivity, yeah, in EFT, yeah, which is related in this case to causality of the theory. Okay, so let me stop here because it's already time, I guess. I will continue maybe with this introduction on the following lecture, yeah, and then I will move to SMEFT.